Hello. So we talked last week about polarization, and in particular we looked at Polaroids which polarize light. And just as a reminder, polarization means that a transverse wave moves in one particular direction, rather than that the motion goes in any direction that is perpendicular to the propagation direction. So another example that we started talking about where polarization occurs is in reflected light rays. And in particular, we look at the reflection of light going from air into water. And we can distinguish two polarizations. The first polarization is perpendicular, and the second polarization is parallel to the so-called plane of incidence. And plane of incidence is the plane that contains the incident ray, the reflected ray, and the refracted ray. So with these two polarizations, the one where the electric field vector is parallel to the plane of incidence, meaning like this, and where it is perpendicular to the plane of incidence, meaning that it goes out like this. So if we look at the reflected amplitude compared to the incident amplitude, we get two formulas that correspond to those two cases. The one is the perpendicular case, and in this case, the reflected over the incident amplitude is given by this expression, which depends on the indices of refraction, n1 here and n2 here, and the cosine of the angle of incidence and of the angle of refraction. And of course, the angle of reflection is given as the same as the angle of incidence. Now, the interesting case is where the reflected ray is perpendicular to the refracted ray. And that is interesting because in that case, the cosine of the refracted angle is the sine of the reflected angle or of the incident angle, and the sine of the refracted angle is the cosine of the incident angle. And that is the case because sine of 90 degrees minus some angle alpha equals cosine of that angle alpha, and cosine 90 degrees minus alpha equals sine of alpha. So it's simply because of that fact of trigonometry. So if we now look at the one of these cases, the parallel case, then we notice that if the incident angle or the reflected angle is the same as 90 degrees minus the refracted angle, and using Snell's law, we note that n1 cosine theta refracted equals n1 sine theta incident. And then Snell's law says this must be equal to n2 sine theta refracted. And that, using again those two trigonometric identities, tells us that this is n2 cosine theta incident. And therefore, since this equals that, that means this equals that, and therefore there is no reflected amplitude at all for the parallel case. So if you have unpolarized light, meaning an equal admixture of the perpendicular case and the parallel case as the incident light, then the parallel case disappears and we are left with only the perpendicular case. And that means that we have 100% polarization perpendicular to the plane of incidence for the reflected light. And that can be made use of in photography. We also talked about that 2 days ago or 3 days ago. So we can eliminate or reduce the intensity of reflected light by applying a polarizer to the camera. And for example, we can therefore on a photograph we can then show or emphasize the ground compared to the reflection from the surface of a pond. That works because we can greatly reduce the light intensity from the reflected light. Now, if we want to know what is this magic angle where polarization is 100%, which is sometimes called the polarizing angle or the Brewster angle, then we can look at the tangent of the incident angle, which is the sine of the incident angle over the cosine of the incident angle, or the sine over the incident angle over the sine of the refracted angle. And then we apply Snell's law, and that gives us that this is n2 over n1. And so, in other words, tangent of this polarizing angle must be n2 over n1. So if we calculate an example, what is the polarizing angle for the case air and water? And we find out that it's 53.1 degrees from the two indices of refraction, 1 and 1.33. And if we then find the refracted angle from Snell's law, we find that it's 36.9 degrees, and indeed both angles add up to 90 degrees. So polarization has many applications. In particular, one that is interesting are liquid crystal displays. So liquid crystals is an organic material which is neither fully solid nor fully liquid, at room temperatures at least. And it consists out of long molecules, and they tend to have random positions, but not random alignments. They tend to align themselves to their neighbor's direction. And if we now use such an LCD material and sandwich it between glass plates, and let's say the glass plates have scratches to give them a preferred direction, then those molecules that are next to the glass will align themselves to the direction of the scratches. And if we have the two glass plates with orientations of 90 degrees with respect to each other, we form a kind of twisted structure. And the way this looks like is like this. So we have a vertically scratched glass here, and the molecules tend to align themselves close to those scratches, and we have horizontal scratches here, and that means molecules will align themselves horizontally here, and in between they will align themselves to their neighbor, and sort of we get a gentle rotation of the vertical to the horizontal. And if we have such a twisted structure, then it is kind of like a twisted Polaroid. Polaroids were also long molecules, and we learned that the Polaroid lets one polarization through because the other polarization does work on the charges in the molecule, and that is easy going along the molecule, but not easy going perpendicular to it. So basically we have kind of like a whole bunch of polarizers, and if we now put an explicit polarizer on either side with the axes aligned with those of the scratches, then light will get through because the polarization of the light, which is originally vertical, will be rotated by this twisted structure until it's horizontal, and then it goes through the horizontal polarizer just fine. So as long as we leave this structure alone, light will be able to pass through the LCD. But if we now apply an electric voltage, then those molecules which have charges on the end, or which will get induced charges at the end from the voltage, they will rather align themselves end to end and ignore the scratches on the glass. And therefore we destroy those twisted structures, and that means that the polarization of the light going through is no longer rotated. And therefore we have two crossed polarizers, and the LCD becomes dark. So the neat thing about LCD displays is that they need very little power, because all you do is you apply a voltage, it destroys the structure. And it's kind of like just charging a capacitor and discharging it again. So it requires very little power, and yet you can turn that into displays, for example, in pocket calculators like this. So such simple LCDs use segments of liquid crystals, and those segments are then used to display numbers or letters. More sophisticated LCDs are pixelized. For example, this little image of a man with a cylindrical hat. And such pixelized LCDs are used in flat screen TVs, and there they are usually illuminated by, from the back, either by LEDs or by thin fluorescent tubes. And you can get color in such pictures. I mean, those are basically just black and white pictures, but you can get color by dividing each pixel into 4 subpixels and then supply them with color filters, red, green, and blue. And by the way, both the LED and the LCD TV sets, they both share an LCD. It's LED or LCD just refers to the type of illumination, not to the basic technology. So another aspect of polarization is if we look at Rayleigh scattering of light in the atmosphere. So if light passes through the atmosphere, it impinges on the air molecules in the atmosphere, and it jiggles the charges of those molecules, and then often the molecules re-emit the light, but in a different direction, and that is called light scattering. And the reason why they re-emit is because the charges wiggle around, and therefore we have accelerating charges, and they are the origin of a dipole electromagnetic field. So just like an antenna, basically. So if we have a solar ray here, and it hits an oxygen or nitrogen molecule, then if the molecule is oriented in the right way, it can be vertically oriented or horizontally oriented, then it will start oscillating, and then it will eventually re-emit photons. However, because antennas or dipole antennas don't emit in the direction of oscillation, if it is a vertical molecule, it will not be able to emit a photon that is going downwards. While if it's oriented horizontally, it can emit light that is going downwards. And therefore we get a polarization effect that is maximal at right angles if we look at the solar ray with respect to the scattered photon. So at right angles, we only get one of the 2 possible polarizations. And an observer sitting down on the surface of the Earth is seeing polarized light. And that is useful to animals. For example, it is an aid in the navigation of bees when they try and find flowers. And you can get a similar view by wearing Polaroid sunglasses. And if you have them, then on a sunny day, I invite you to go out and find the dark band across the sky. And the advantage is, even when the sun is obscured by clouds, you can still find the position of the sun that way. Another interesting thing is about Rayleigh scattering is that it is proportional to the inverse fourth power of the wavelength. And that is true as long as the scattering molecule is, the size of it is much smaller than the wavelength of the light. And that means that blue light is more readily scattered than red light would be. And as a consequence, the sky looks blue to us. So the color of the sky is nothing else but the scattered photons from the sun, which are predominantly blue. And if we look at the sun itself, when it's high in the sky, all we see is white because it's too bright. And also the amount of atmosphere the sun rays go through is not very much. But at sunset, when the sunlight is passing through a lot of atmosphere, then most of the blue photons are scattered away, and what is left is red, and therefore sunsets are red. Then finally, the color of clouds is white or gray, and the reason for that is that the scattering in clouds is done by much larger agents, for example, water droplets or crystals, and those are much bigger than the wavelength of the light, and there's no Rayleigh law anymore. And in fact, the amount of light scattering is independent of wavelengths. So let me try and demonstrate the Rayleigh law for light scattering using a little bit of milk mixed into water. So I have here a jar of water, and we are looking at light that goes out through the top. And let me now put a little bit of scattering agents in there. Stir that in. It's maybe not quite enough yet. Milk. This is just, actually it's creamer.
Vanilla or hazelnut?
And I'm trying to increase the scattering in the water of light to see the color change of the transmitted light. And if you look at it, you already see that it's turning a little bit orange. Put a little bit more in there. So it starts to look like a sunset. Let me turn off the lights so that it becomes a bit easier to see. So we definitely see that the color of the light that is going through is changed to orange. A little bit more in there. What is not as easy to see is if you look at the jar from the side, it looks a little bit bluish. Unfortunately, the overhead projector doesn't have too many blue photons in there to begin with, and therefore that is a fairly faint effect. But it looks like just a slight hint of bluish light if you look at it from the side. Let me turn on the lights again. So let me summarize the chapter about diffraction and polarization. Oh, sorry. Here we go. First of all, light diffraction means that light waves bend around obstacles, and it produces a diffraction pattern of constructive and destructive interference. And we saw the diffraction pattern of a narrow single slit of width d, and there's a bright white central maximum, and there are minima if the sine of the angle under which it is viewed equals an integral number times the wavelength divided by the diameter d. And that is true for an integral number plus minus 1, 2, 3, but not 0. And the wave nature of the light limits resolutions that you can obtain with optical instruments. The so-called Rayleigh criterion tells us that the diffraction pattern due to a circular aperture limits the resolution. And the criterion is that if you have two different objects, then the first minimum of the airy disk, the circular diffraction pattern of the first point, overlaps the central maximum of the second point, then those 2 points are at the limit of being able to be resolved. And that first minimum for the circular case is for sine theta equals 1.22 times lambda over d. And usually theta is small, so we can approximate sine theta with theta. And as a consequence, we observe that the largest useful light microscope magnification is about 600 times. If you magnify beyond that, then all you see is diffraction patterns rather than the object that you're studying. So if we combine many different slits or reflective lines, we produce a diffraction grating. And they produce sharp and bright maxima for sine theta equals an integral number times lambda over the line spacing d, where this time m can be 0, plus minus 1, plus minus 2, plus minus 3, and so on. And such diffraction gratings are used in spectrometers to separate and measure different wavelengths. For example, emission line spectra. Then X-rays are electromagnetic waves with very short wavelengths produced by collisions of high voltage accelerated electrons with glass or metal targets. And they're useful, or their diffraction is useful to study crystal structure, such as the double helix of the DNA molecule. And then finally, unpolarized light means that the electric field oscillates in all transverse directions, while plane-polarized light means that the electric field oscillates in one plane only. And unpolarized light passing through a Polaroid sheet becomes polarized. And if you have two Polaroid sheets, then the first one acts as a polarizer to turn the light into polarized light. And the second one is the analyzer. And if you tilt the two axes of the two Polaroid sheets by an angle theta, then the intensity passing through is proportional to the cosine square of that angle. And reflected light from an optical thinner into an optical denser medium becomes polarized, and there's 100% polarization at the so-called Brewster angle, which is, for that polarizing or Brewster angle, the tangent of that angle is equal to n2 over n1. So this concludes the classical physics portion of this course. So all what we've learned up to this point is what people knew in the 19th century. And at that time, most physicists believed that there's nothing more to be discovered. And the only thing you can do is measure things more precisely and refine theories a little bit. So basically, Newtonian mechanics and Maxwell's equations should describe the entire world. And all phenomena can be thus explained. Unfortunately, they were wrong, and the best was yet to come. And there were two revolutions that took place. One was was special relativity and eventually general relativity, which modified Newtonian mechanics and in one direction. And the other one was quantum theory, which modified both Maxwell's equations and Newtonian mechanics. And quantum theory made possible the invention of the electron microscope. And this is an electron microscope picture. And in fact, those little green bastards are Giardia bacterium in a human small intestine. And if you ever went hiking and encountered some of these, then you know what I'm talking about. So at the time, even in the 19th century, there were a few puzzles that remained, which were kind of difficult to explain with Maxwell's equation and Newtonian mechanics. But people just thought they didn't try hard enough. And one of those obstinate little problems was the black body radiation. So when physicists talk about a black body, it doesn't mean it's very black. It just means it is a system that is able to absorb all radiation that you throw at it. So that, for example, can be a pinhole. Any radiation that goes in there disappears in there. But it can also be, for example, a star, like the sun, because whenever you have radiation hitting the sun, it doesn't come out. The sun just shines with its irradiance independently of what radiation hits it. So black bodies that have a finite temperature, finite meaning that temperature is bigger than 0, they emit a radiation spectrum. In fact, all black bodies do. And that spectrum depends only on the temperature of the black body. And here are some examples of black body spectra for 3,000 degrees Kelvin, 4,500 degrees Kelvin, and 6,000 degrees Kelvin. And I'm plotting here the frequency at the top of the electromagnetic waves and the wavelength at the bottom. But we can also look at just one at a time. And right now I'm at a temperature of 4,800 Kelvin, which is a little bit hot, so let me make it cooler and start with something like the environment of Earth. Zoom in a little bit here so that we can see. And so at room temperature, the black body radiation peaks at a relatively long wavelength, so something like 10 microns or so. And that radiation is called infrared radiation or heat radiation. If we now make it a little bit hotter, let me zoom out here. For example, like a nice pizza oven, then we see that the wavelengths become shorter and also the amount of radiation becomes far larger. So if we go to higher temperatures, say about 1,000 degrees, the light starts to, the radiation starts to wander through the visible spectrum. And therefore, if you heat, for example, steel or iron, then it starts to turn red, and so we call it red hot. As we go to higher temperatures, again, radiation becomes far more intense and wavelengths become shorter. And now multiple wavelengths in the visible spectrum participate, and the object starts to appear white. So white hot is hotter than red hot. You can also see the approximate color of the radiation by this little star here. So if I go back to the 1000, then you see it's very red, and as I'm going to higher and higher temperature, it starts turning white. When we hit the operating temperature of your typical light bulb, then you see that even though you produce lots of visible light, you produce lots more of heat. And that's why the Edison light bulb is rather inefficient. Most of the radiation it produces goes into heating your apartment rather than lighting it. If we increase the temperature further, then eventually we reach the radiation temperature of the sun. This, by the way, is not the core temperature of the sun, which is a lot hotter than that, but just the photosphere, which actually emits the light. And we notice that the solar light spectrum, it peaks at about half a micron in the greenish blue. And the temperature that it corresponds to is about 6,000 Kelvin, or in this case here, 5,745. And if we go to even higher temperatures, then the radiation starts to look very blue. And that would be the case for a hotter star than the sun. Now, one thing that classical physics will readily answer is where is the peak of the spectrum as a function of the temperature. And that is given by so-called Wien's law. And Wien's law states that if you look at the peak wavelength times the absolute temperature, then the product of the two is a constant. And that constant is 2.9 times 10 to the minus 3 meters times Kelvin. So let's look at an example. The example is the sun's surface temperature. So let's estimate the sun's surface temperature given that we know that the solar spectrum peaks at about 500 nanometers. And if we divide this Wien constant, 2.9 times 10 to the minus 3 meters times Kelvin, by half a micron, then we get the radiation temperature of the sun, which is 5,800 Kelvin. So when one tries to understand classically why black bodies radiate, then you imagine that it must come from applying Maxwell's equation to the molecules that make up the black body, which, for example, can be the surface of an oven, or it can be the sun, or whatever. However, once you try to be quantitative, for example, the Rayleigh-Jeans theory, a classical theory, then you see that the spectrum it predicts is just keeps rising forever as you go higher in frequency. And that's rather bad for many reasons. One particular one is that if you integrate the total amount of energy, you come up with infinity. So that's clearly a ridiculous answer that makes no sense. There's also a theory by Wien, the fellow with the Wien law, and that looks much better. It at least gives us a finite amount of radiation energy. However, unfortunately, it disagrees with experiment. And finally, after almost suffering a nervous breakdown, so legend has it, Max Planck found this formula which correctly describes the blackbody radiation. However, he cheated because he allowed only energies as multiples of h times the speed of light divided by lambda. And you can call that the energy quantum. And so energy ought to be continuous. So this is really an incorrect assumption. However, it seems to phenomenologically correctly describe experiment. So what does it mean? So if we assume that molecules are like masses on springs, then we have a simple harmonic motion, and all energies and all amplitudes ought to be allowed. So if we look at the potential energy as a function of position, it looks like a parabola. And so anything on this blue line is an allowed value for the energy. However, Planck assumed that only energies, which is plotted vertically, on those red lines are allowed. And you can sort of number them. So this is the ground level, then this is 1 times h times lambda over c over lambda, and so on. And his original plan in deriving this was he assumed that energy must be multiples of a quantum, but then he wanted to let this little constant h, he wanted it to let it go to 0 and then recover continuous energy as it ought to be. Unfortunately, if he uses a finite value for h, this value, then it fits the experiment. However, as soon as you let h go to 0, it doesn't fit the experiments anymore. And that was rather puzzling. So it seems to imply that indeed only certain energy levels are allowed. So again, classically, all energies ought to be possible. You sort of have an inclined plane, in this case for potential energy. But with Planck's hypothesis, it's sort of like a staircase where each step is h times f. Fortunately, the energy quantum is very small. So even for optical frequencies on the order of 10 to the 14 hertz, one energy quantum is only on the order of 10 to the minus 19 joules. And so one could certainly argue that it might have escaped observation so far, that energy really comes in little steps like this. However, nobody really took these quanta seriously, not even Planck himself. And everybody just thought, well, it's a kind of math trick to obtain the right spectrum, and someday we can do it properly, and we don't need this trick anymore. The only one who actually took it seriously was this fellow. So Einstein looked at this, and he proposed a new theory of light. And this new theory of light is a particle theory of light. So this was rather daring. After 100 years of success of the wave theory of light, he suggested a particle theory of light. And his argument is not only can it explain the blackbody radiation neatly, it can also explain another effect, which is called the photoelectric effect. And this photoelectric effect is if you shine light on a metal surface, then the surface starts to emit electrons. And so you can construct a so-called photocell where you apply a voltage to a metal surface. So here we have anode and cathode. And then you evacuate it so that electrons have an easier time propagating. And when you shine light on it, you observe a current. And that current varies with the potential that you apply. So for the photoelectric effect, the electron's kinetic energy and thereby the speed can be measured by stopping them in an electric potential. So when the voltage is just right, that the electrons don't propagate anymore and the current therefore becomes zero, then the maximum kinetic energy of the electrons must be equal to the electron's charge times the applied voltage. So now we can look at it with the predictions of the wave theory. The wave theory tells us that the light intensity is proportional to the square of the electric field. And that means if we have larger light intensity, we have a stronger electric field. And if you have a stronger electric field, it pulls more strongly on the electrons. And therefore, the electron's kinetic energy must increase. And of course, it will start ripping out more electrons. The frequency of the light is irrelevant in this process. It shouldn't matter. So we can sort of draw a little picture of this. So here we have the electrons in their bound state at some potential energy. When they're in their free state, they're at a higher potential energy, and the potential difference we call W0. And the amount of electrons that we liberate and their energy depends on the electric field amplitude, which can be controlled by the intensity. So in particular, if the electric field is large enough that it can overcome this potential boundary, then electrons start to be emitted, and otherwise no electrons are emitted. For the photon theory, however, we hit the electrons with little particles called photons. And those photons have a particular energy, h times f, like in Planck's hypothesis. And if f is big enough, then it will kick those electrons strongly enough to lift them up to the potential W0. And so, in other words, the intensity just controls how many electrons are appearing, but not whether they appear and also what their kinetic energy is. That is controlled by the frequency. So Einstein's theory of light predicts that the kinetic energy starts at zero at some frequency f naught, where f naught is given by the condition that W naught equals h times f naught. And then it continuously rises with the frequency. And again, larger light intensity just means more photons and therefore more emitted electrons, but not larger Kmax. And of course, if HF is smaller than W0, then no electrons are emitted. And so the big question is, who is right, Einstein or all of physics before Einstein? And the answer is obvious. Of course, Einstein is right. He tends to be. He's almost always right. So Millikan measured the photoelectric effect in 1913, 1914, and they were in agreement with the photon theory. And that was the birth of quantum mechanics, and Einstein received the Nobel Prize. So with that, let me conclude. Thank you.